Welcome back. Tesla Motors engineers made a stunning design choice when they developed the Tesla Model 3. They abandoned the conventionally used and well-proven induction motors and replaced them with the new kind of motor, called Internal Permanent Magnet Synchronous Reluctance Motor, or Tesla Model 3 motor. These motors have totally different design, making use of both magnetic and reluctance action. Tesla Motors has started replacing the induction motors in their Model S and X with the new motor as well. In this lecture, I will go through the journey of Tesla Model 3 motor and what makes IPM Syncrm motors so special. Before exploring these new motors, let's see why induction motors are not up to the mark. Every motor has a rotor and stator arrangement, clearly as you can see here. The rotating part of the induction motor is arrangement of conducting bars. Once stator creates rotating magnetic field, this fluctuating field interacts with the rotor bars and generates current in the rotor bars. The induced currents and the RMF interact, imposing force on the rotor bars, and the rotor starts to spin as shown here. But there is an issue. Suppose for long drives at cruise speed, losing 3% to 4% of energy to generate currents in the rotor bars is definitely not efficient. That's why, to overcome this issue, Tesla Models is replacing this motor in RWD and AWD cars with IPM Syncrm motors for better efficiency. I will explain to you in details about the IPM Syncrm motors, so let's move to it. The IPM Syncrm is a combination of permanent magnet and Syncrm motors, and if we integrate it by placing the permanent magnets into the slotted cuts of the Syncrm motors deep within the iron core. To understand it in simple manner, I will explain both types of motors here. First is permanent magnet. The permanent magnet motors, or PM motors, works on the basics of attraction between two magnetic fields. They produce a good starting torque from the same motor volume. This is more efficient when you operate them using the controller, and they do not experience energy loss in the rotor. But the PM motors have an issue. When the car cruises down the road at high speeds, permanent magnets motor have a terrible performance because the generation of back EMF in stator coils. The back EMF is induced when the magnetic field lines produced by the permanent magnets link with the stator windings. This is clearly a reverse voltage to the stator's supply voltage. The higher the rotor speed, the more it produces the back EMF. One more disadvantage is that the magnets results in the magnetic eddy current losses, which increases the heat in the machine, and this is not favorable. Keep this explanation in mind. Now I will explain the second type of motor. Now we will understand how Tesla Motor have overcome these issues by using Syncrm motors. For high-speed operation, Tesla engineers made use of iron's reluctance property. Here, iron gives a less opposition to magnetic fields than air. Using this phenomenon, Syncrm motors generate rotation. To get this rotational motion, we cut slot in the rotor, and this motor position, the rotor is in high reluctance state as shown here. However, if the rotor is turned by 45 degrees, it will face very low reluctance as shown. The rotor always has a tendency to attain a low reluctance state. Therefore, if the magnetic field rotates, the rotor will rotate along with it, so that the rotor can always be in a low reluctance state. The rotor's rotation speed will be the same as the RMF speed. The torque produced by this phenomenon is known as reluctance torque, and such motors are called synchronous reluctance motors. You have to keep this in your mind that Syncrms can enhance high-speed operations. They don't have back EMF issues, and permanent magnet motors can be designed to perform good at low speeds. Then it is good to integrate the Syncrm technology into the permanent magnet motor. If we do it, this motor can work efficiently. The interesting thing about this design is that the permanent magnet and reluctance part of this motor have totally different behavior in regard to the position of the RMF. Now let's analyze the Tesla Model 3's motor. The total torque that if the RMF angle is around 50 degrees will get maximum torque from the motor. So Tesla Motors engineers made sure that when you start the car, the RMF angle is around 50 degrees, which will guarantee maximum torque production using both reluctance and permanent magnet torque. But after a certain high speed, the back EMF show up. To overcome this, field weakening is done. The permanent magnets in the IPM Syncrm motor still have some effect on the stator, producing the back EMF at high speeds. To overcome this issue, we can align the RMF opposite to the permanent magnet field. The RMF weakens or almost cancels the permanent magnet field. This way, even at high speeds, such motor won't produce much back EMF. Obviously, at this stage, the torque production will mostly come from the reluctance effect.